Because the best way to understand why something is failing is to understand how it works in the first place. We often forget that the entire Earth is actually connected by a vast, interconnected body of water. And the AMOC holds that system together like a giant mixing mechanism. It distributes water, heat, nutrients, dissolved gases, and microorganisms around the Earth through ocean currents. Simply put, the AMOC is a complex but orderly network of countless currents and eddies. This entire system forms a giant vertical circle across the Atlantic Ocean, which, when viewed on a map, might look like a tangled string or spaghetti. There are different types of currents at work here. Tidal currents, which are created along the coast by the sun and moon, surface currents, which are driven by the wind, and deep currents, which flow slowly along the ocean floor. These deep currents are the most important to us because they are controlled by differences in ocean temperature and salinity. This process is called the thermohaline circulation, where thermo means heat and haline means saltiness. This is a conveyor belt that circulates water in long cycles within the Atlantic Ocean from north to south and back north again. Warm water moves north along the ocean surface, while cold, deep water moves south. This brings heat and nutrients to cooler areas and transports carbon deep into the ocean. This process begins on the east coast of North America. The Gulf Stream, which is part of the AMOC, carries warm water through the Florida Straits to the Grand Banks of Newfoundland. The North Atlantic Current then flows towards Europe and the Norwegian Sea. When the warm water reaches Greenland or the Arctic, it loses heat to the atmosphere and condenses and cools. This cooling results in the formation of sea ice. As ice forms, salt is trapped in the water, making it denser. The denser water sinks to depths of 2,000 to 3,000 meters and flows south. This is where the term overturning of AMOC comes from. This creates a vertical overturning of the entire ocean basin as the water rises to the surface and warms up again, completing the cycle. Almost like a central heating system, the AMOC moves 17 million cubic meters of water northward every second, the equivalent of about 7,000 Olympic-sized swimming pools. This results in 1.2 petawatts (PW) of heat being transferred, which is 100 times more than the total global energy produced by all of Earth's energy sources. It is important in regulating climate around the world. This whole process is slow. It takes about 1,000 years for a given cubic meter of water to complete this cycle. But it is slowing down now, which is causing problems. Now, let's clarify the difference between the AMOC and the Gulf Stream. The Gulf Stream is a part of the AMOC, not the entire system. It starts off the coast of Florida, runs along the east coast of the United States and Canada, and heads toward Europe. The Gulf Stream keeps the climate warm in Europe. For example, in England, we enjoy a relatively warm climate, even though it is not close to the equator. Without the Gulf Stream, temperatures in the UK would be 3 to 4 degrees Celsius cooler, and mainland Europe would be at least 10 degrees cooler. The Gulf Stream carries warm water from the South Atlantic northward through the AMOC. When the main current ends, the warm water moves northward along a shorter path. During this time, the warm water loses heat through evaporation, leaving behind cold, salty water that comes into contact with the fresh water of the North Atlantic. The Gulf Stream is formed by large oceanic gyres and strong air currents. There are 5 oceanic gyres on Earth: the North and South Atlantic, the North and South Pacific, and the Indian Ocean gyres. The Gulf Stream is part of the North Atlantic gyre. 10:06. Now we turn our attention to the AMOC and its impact on climate. As we said before, everything is interconnected, especially the large cold landmass, which has been the only cold place on Earth for the past 20 years. It's not just the upper layer, it extends to a depth of 2,000 meters. This is evidence of a slowing AMOC. The salinity in the region is also decreasing, reaching its lowest level in 120 years. As a result, the water is less dense and has difficulty sinking and mixing with other waters. This is very important for the stability of the AMOC. The amount of ice in the ocean is decreasing due to a significant increase in greenhouse gas emissions. Modern climate models and observational analyses show that the recent warming hole in the North Atlantic is anthropogenic and is related to greenhouse gas emissions. The main reason is the reduction in northward ocean heat transport. To understand human impacts, we need to look at past climate conditions. This information comes from proxy data, such as ice sheets or seafloor sediments, which slowly accumulate and leave traces of past climate. The ratio of oxygen isotopes found in microscopic skeletons is present in most deep-sea sediments. It provides a record of past surface water temperatures. The size of the particles in the sediments on the sea floor reveals the speed of the currents above and helps us reconstruct past sea surface temperatures and other parameters. The researchers say that the AMOC has been weak for a long time, since the early to mid-20th century. Climate models have long predicted its decline due to global warming. Paleoclimatic data also point to human activity, as the weakening of the AMOC coincides with a period of modern warming. In short, humans have exacerbated this instability. We can see several changes. Greenhouse gas emissions and Arctic amplification have increased. The water cycle has intensified. Extreme weather events such as floods and droughts have increased. Evaporation has increased in the subtropics, and precipitation has increased at high latitudes. Sea ice is melting. The Greenland ice sheet is melting at a rate of about 270 billion tons per year. As a result, the North Atlantic is becoming less salty. Fresh water dilutes the salt water, which creates a salt advection feedback, a positive feedback that reduces the strength of the AMOC. In 1961, American oceanographer Henry Stommel observed that the salinity of the North Atlantic creates a tipping point for the AMOC. The AMOC flows because the North Atlantic is salty, and it stays salty because the AMOC flows. This is a self-sustaining feedback mechanism. If the salinity decreases due to freshwater inflow, the water density decreases and the AMOC slows down. This brings in even less salt, which weakens the AMOC even more. The AMOC has a history of stability. It has collapsed before, and its collapse has been linked to some extreme climate events. We are still in an interglacial, but the climate of the last ice age was not stable. To understand the behavior of the AMOC in the past, we can look at paleoclimate data, about 100,000 years of data. Studies of ancient climates have shown that there were periods of sudden warming and slow cooling, called the Dunsgaard-Oshgar D/O events. These events occurred during the last ice age and were likely caused by instability in the AMOC. Data from ocean floor sediments and Greenland ice sheets show that this cycle of warming and cooling has recurred over the past 60,000 years.
The green line represents the sediment data, and the blue line represents the ice core data. Interestingly, when the blue and green lines drop rapidly throughout the period, they coincide with the Henrik events, or numbered D/O events marked in red. This suggests that an unstable AMOC is likely the cause of this dramatic, abrupt change. During the Younger Dryas, about 12,500 years ago, the AMOC suddenly slowed down. This caused temperatures in the northern hemisphere to drop to near glacial lows. This event was caused by the melting of the Laurentide ice sheet, which caused massive icebergs to suddenly flow into various parts of the North Atlantic. These flows are known as Henrik events. 1617. At certain times, the ice sheets release large amounts of fresh water into the North Atlantic. We see evidence of these events in ocean sediments, which are deposited as layers of coarse-grained sediments from the land. These layers, which are continuous across a large area of the North Atlantic, bear evidence of an increase in the number of icebergs carved from the Laurentide ice sheet and the southward spread of cold polar waters. Scientists have hypothesized that this freshwater influx reduces the salinity of the ocean so much that it slows down the formation of deep water. This slows down the AMOC. Since the thermohaline circulation is important for transporting heat northward, its slowing down cools the North Atlantic. Later, as the freshwater influx decreases, the salinity of the ocean and the formation of deep water increase again, and climate conditions gradually return to normal. Hopefully, by now, you understand the basic idea of this big and complex problem. Now we will look at the big question: when will it break? Note the use of the word "when" here. What surprised me most while recording the video was that so many different papers have been written about the fragility of the AMOC. The answers to this question vary widely among researchers, but they almost all agree on one thing. If the current trajectory continues, the question is not will it break, but when it will happen. A few years ago, the Intergovernmental Panel on Climate Change, IPCC, generally agreed that the probability of crossing the tipping point this century was less than 10%. However, the latest, sixth report from the IPCC shows that this probability has increased significantly. 1812. Under low-emission scenarios, the AMOC could weaken by 4% to 46% by 2100, depending on the model. Under high-emission scenarios, the decline could be 17% to 55%. But some conflicting reports suggest that the AMOC could collapse by 2025. So what is really happening? Who is right and who is wrong? Excellent question. In reality, it is not that simple. A lot of it depends on how the AMOC is modeled and what physics and factors are taken into account. Most models, outside of paleoclimate data, are limited by the lack of actual measurements of the AMOC over a sufficiently long period of time. The IPCC report uses the CMIP6 model, which is made up of about 100 separate climate model runs from 49 different modeling groups, Critics have pointed out that the model overassumes the stability of the AMOC. When the AMOC was given as input, it was tuned to be stable. As a result, it does not accurately reflect the realistic scenario of AMOC decline and results in a conservative estimate. Many critics say this is simply overly conservative. On the other hand, there are papers that say with 95% confidence that the AMOC could collapse between 2025 and 2095. How did they come to this conclusion? These scientists used a different type of model called reanalysis, which attempts to go beyond the short observation period. For this, they used North Atlantic Subpolar Sea Surface Temperature, SST. However, using SST as a measure of AMOC collapse is controversial in scientific circles. Actual observations of the AMOC since 2004 do not match this estimate. The 5 data points that the researchers show were collected by ship surveys over several years. This can give a misleading idea of the collapse of the AMOC. The authors themselves admit that there is a large uncertainty in their conclusions. Let's get back to the big question of when the AMOC will collapse. The paper using SST suggests a mean time of 2057. Other papers support this, showing a probability of collapse between 2037 and 2064, 10 to 90% confidence interval, with a mean time of 2050. I'll let you decide for yourself on a specific date, but one thing seems certain. If we continue at the current rate of global warming, we will have catastrophic events in our lifetimes. A complete collapse of the AMOC would be a planetary catastrophe. There's no denying that. But what if this system collapses? The situation in Europe doesn't look particularly good. Let's start there. European cities will see temperatures drop by 3 to 10 degrees Celsius in a few decades, and the impact could be even more severe in some areas. For example, February in Bergen, Norway, will get 3 to 5 degrees Celsius colder per century. It's not that a new ice age will start in 2 weeks, but the North Atlantic region, and especially Europe, will cool significantly. The situation in England, Scotland, and Ireland could be as difficult as in northern Canada. Winter storms will increase in intensity across Europe, and rainfall will decrease significantly in Western Europe. This will have a major, lasting impact on agriculture in regions such as France or Great Britain. It will be just like trying to grow potatoes in northern Norway. But it's not just Europe that will be affected. Sea levels in the Atlantic Ocean could rise by up to 70 centimeters, submerging many coastal cities around the world. This will make many densely populated areas uninhabitable. Scientists also predict that the tropical rain belt will shift southwards. This is a bad sign, as the rain will move to areas that are not used to the extra rainfall. This will lead to drought in some areas and flooding in others. The Amazon rainforest will also see major changes. Rainfall in the Sahel region will decrease, and the summer monsoon in Asia will weaken. As the northern hemisphere cools, the southern hemisphere will gradually warm. Heat from the Pacific Ocean will not be transported to the North Atlantic and will instead be trapped in the tropics, causing temperatures there to rise dramatically. This will also reduce the ocean's absorption of CO2. Because the AMOC sinking in the North Atlantic sends a lot of CO2 into the deep ocean, where it is safely stored away from the atmosphere. We don't need more carbon in our atmosphere right now. The AMOC sinking in the North Atlantic Ocean sends a lot of CO2 into the deep ocean, where it is safely stored away from the atmosphere. We don't want more carbon in our atmosphere right now. The cooling of some parts of the world might not be so bad. Since we always hear about the world warming, maybe the decline of the AMOC could have some positive effect on the contrary. 23:35. But the truth is, we don't think there is any place where things would be better. Rather, it would have the opposite effect. If it were just a matter of average temperatures, a place like Germany would be able to maintain some balance due to its location.